Hello everyone, good morning. So, since I haven't actually received any questions from you guys about differentiation, I'm gonna assume that everyone is okay so far. If there's anything you want to ask, now would be a good time. You can just send it to me. Otherwise, we'll continue with the last part of differentiation, parametric differentiation. And then after that, we'll do one small portion of integration, and I shall leave you to it. I haven't uploaded the RCA papers for implicit differentiation yet, so let me do that now real quick. Okay, one sec. It's over here. If the music's a bit too loud, let me know and I'll drop it a bit. Or if you find it too distracting, I'll turn it off. Okay, so there we go. I've uploaded the RCA questions for parametric differentiation on Google Classroom. It's actually a very short chapter. Okay, let's get started. Let me get rid of this. Move this here. Okay. Right. So parametric differentiation, I think the best way to show you how to do this is to jump straight into one of the questions. So let's say you are given x is equals to t squared and y is equals to 2t. Right, so usually we're given x in terms of some function of t, y in terms of another function of t, and then they will ask you to find dy dx. So how do we do that? Well, we don't have y in terms of x. So what you could potentially do is you get rid of the t's by substituting one equation into another. So that is one way of doing it. However, I would recommend using the chain rule instead. So you could write dy dx is equals to dy dt times dt dx. You can see that the dt's here would cancel out, so you still end up with the original expression dy dx. So dy dt is going to be from this guy here. So dy dt is 2. You're differentiating with respect to t. And then from this guy, we can find dx dt, which is 2t, which tells you that dt dx must be equals to 1 over 2t. So putting that in here and this in here, we're going to get 2 times 1 over 2t, which gives us 1 over t. So now we have our gradient in terms of t. Okay. And let's say for the second part of the question, they want you to find the equation of the tangent to the curve at the point t squared 2t. Alright, so what you want to do here is remember that the tangent is actually a straight line. So a straight line has an equation y minus y1 equals to mx minus x1, right? Where the m here is the gradient of the tangent. So in this case, m is dy dx, which happens to be 1 over t. So we can put in our coordinates, which is going to be 2t here, and 1 over t here, and then x minus t squared. And then you're done. That is the equation of your tangent. You can simplify this a bit more if you want. So you get y minus 2t equals to x over t minus t. Move that over here, you get 1 over tx and then minus 3t. There we go. And then part 3. So find the equation of the tangent when t is equals to 3. This t here is usually what they refer to as the parameter. That's why this part of the chapter is called parametric differentiation, because you're differentiating the equation with respect to a common parameter. Okay, so all you gotta do is start with your equation of the tangent, and then when t is equals to 3, you just substitute that in, and you're done. That's it. Okay, that's essentially it. You don't have to worry about sketching the graph because they will never ask you to do that in the actual exam. Alright, so let's do another example. Example 2. Let's say now you are given x is equals to 4 cos theta and y is equals to 3 sine theta. So now your parameter is theta. So for the first part, they say find dy dx in terms of theta. Okay, so you just do the same thing. Dy dx equals to dy d theta times d theta dx. Just use the chain rule. So from here, dy d theta is going to be 3 cos theta. And from here, dx d theta is going to be negative 4 sine theta. So putting that in here, we are going to end up with 3 cos theta times 1 over negative 4 sine theta. Putting these two guys together, we get 3 over 4 and then cotangent theta. Okay, and we are done. So, for the next part, find the equation of the normal. Let's see here, find the equation of the normal at the point 4 cos theta 3 sine theta. So first, to find the normal, it is a straight line, so we're gonna have to use y minus y1 equals to mx minus x1. However, the gradient here is the gradient of the normal. So this is the gradient of the normal. And how is that related to the gradient of the tangent? Gradient of the normal is equals to negative the gradient of the tangent, the negative reciprocal of the gradient of the tangent. So you have to leave it like this. Okay. So let me just move that down here a bit. So putting in our coordinates, we get 3 sine theta here. And this guy is going to be negative 1 over bracket negative 3 over 4 cotangent theta. And then x minus 4 cos theta. Simplifying this, we get 4 over 3 tangent theta. And then x minus 4 cos theta. And there you go. That's your equation of the normal. Okay, so find part 3, find the equation of the normal at theta equals to pi over 4. Okay, so what do we do here? We just gotta substitute this into our thingy from earlier. So 3 sine pi over 4 equals to 4 over 3 tangent pi over 4 bracket x minus 4 cos pi over 4. There. Okay, so use your calculator here. Y minus 3 root 2 over 2 equals to tangent pi over 4 is 1. And there we go, done, finished. Then for part 4, find the coordinates of the point where theta is pi over 4. So when theta is pi over 4, we actually end up with this equation here. Right? So we also can work out the coordinates y and x by taking this guy and substituting it into the original equation right here. So the x coordinate would be 4 cos pi over 4. The y coordinate would be 3 sine pi over 4. So both of these are root 2 over 2, so we get 2 root 2. And this guy would be 3 over 2 root 2. Therefore, the coordinates would be 2 root 2, comma 3 over 2 root 2. There we go. That's pretty much it, really. Okay, let's do one more example. This one is going to involve the stationary points. So let's do that down here. Okay, so for this third example, find the stationary points of x equals to 2t plus 1 and y equals to 3t minus t squared. Find the stationary points and their nature, whether it's a maximum or a minimum point. Okay, so to find the stationary point, we need to equate dy dx to 0, right? That's what we have been doing since AS. So first we got to find dy dx. So using the chain rule, dy dx is dy dt times dt dx. So from this guy here, dx dt is 2. From this guy, dy dt is 3 minus 2t. So taking two of those. We're gonna chuck that in here. We're gonna get 3 minus 2t, and this one is 1 over 2. Okay, so now we're gonna equate this to 0 because we're trying to find the stationary point, which tells us that hang on, let me just check something. 3 minus 2t, yep. Okay, yep. Okay, so equate that to 0, and then we solve for t, so t is going to be equals to 3 over 2. Right then. Wait a minute. Oh, I messed up. This one should actually be t cubed, not t squared, which means this would be 2t squared. 2t squared, so this guy would be t squared. Yep, okay. So t should actually be plus minus square root of 3 over 2. So we actually have two stationary points. So the first stationary point is at, okay, let me just write here. First stationary point at t equals to positive square root 3 over 2, which means x must be equals to 2 times square root 3 over 2 plus 1. So putting that into calculator, we get root 6 plus 1. And your y coordinate is going to be 3 times root 3 over 2 minus root 3 over 2, and the whole thing is cubed. Okay. So we end up with 3 root 6 over 4. There we go. So that is our first stationary point. And then our second stationary point is going to be at t equals to negative square root 3 over 2. Okay, so that means our x coordinate is going to be negative of that, so 1 minus root 6, and y is going to be then we're going to end up with negative 3 root 6 over 4. There we go. Okay. So, having worked out our two stationary points, how do we find the nature of these points, whether they are maximum or minimum? Well, what you could do is, I'll show you two ways of doing this. The first way, which is slightly tedious, involves finding the gradient right before the given x coordinate. So let's say this x coordinate is, root 6 plus 1, okay? And maybe your curve looks like this around the immediate vicinity of that point. So if you find the gradient at a point slightly before it, and you get a negative gradient, and you find a gradient of the point slightly after it, you get a positive gradient, that means this point has to be a minimum point. Okay, for example, let's say okay, let me write it here. When x is equals to root 6, so we are trying to find this point here, okay? What is the gradient? Well, dy dx is going to be equals to let's see. Oh, actually, you know what? since our dy dx is in terms of t, we have to sort of imagine moving t around. So this is our dy dx. Dy dx is this guy here. So if we want to have a... how should I explain this? Okay, fine. Let me do it like this. When x is equals to root 6, that means root 6 equals to 2t plus 1. So t is root 6 minus 1 over 2. So using this, we're going to put that into dy dx. And what does that tell us? Well, let's see, we have root 6 minus 1 divided by 2. Put it into dy dx, we have 3 minus 2 answers squared. And divide that by 2, we get 0.975, which is a positive value. So what it implies is that the gradient of the point before the stationary point is actually positive. So it kind of looks like this. So you see this point here is positive. This gradient dy dx is greater than 0. So usually that is enough to tell you that this is in fact a maximum point. If you want to be certain, you could try checking a point after it somewhere here and make sure that the gradient is negative. So let me just show you how to do that. So let's say when x is equals to root 6 plus 2. Okay, because our x is root 6 plus 1, so we are taking 1 to the left and 1 to the right. So one is root 6, one is root 6 plus 2. What is our t going to be? So root 6 plus 2 equals 2t plus 1. So t must be equals to root 6 plus 1 divided by 2. Okay, so what is our dy dx? Okay, let's put that in. So root 6 plus 1 divided by 2. 3 minus 2 times answer squared divided by 2, and we get negative 1.47, which is less than 0. So we know that the gradient of the point immediately after root 6 plus 1 is, you know, negative. So dy dx is less than 0. Therefore, this pretty much concludes that this is a maximum point. I mean, there is a small possibility that that you might be taking a point that is a bit too far, or too far from the point that you're interested in. So maybe you're kind of looking at something like something like this, and then like this. So maybe this point here is root 6 plus 1. And then when you take root 6, it's actually referring to this point here, root 6. So you find a positive gradient. And then this guy is root 6 plus 2, which is a negative gradient. And then you incorrectly conclude that this guy is a maximum point. So that is a possibility. So what you want to do is you want to try to take a point that is as close to this original point as you can. But even then, it's hard to... Sometimes it's a bit hard to tell whether that is correct or not. So let me show you an alternative method of doing this. So the other thing you could do is what you have been doing. Find the second derivative. What just now is it dy dt supposed to be 3 minus 3t squared? Wait, let me check. Dy dt is 3 minus... Oh yeah, you're right. It should be 3. I forgot to change that. Because originally I put this as squared, and then I later on changed this to a cube. So yeah, you are correct. Contrary to what you might think. It is actually 3. Thank you for pointing that out. Right, so this is already a 3, which means this should be a 1, and that means I've kind of messed up all of this. Hang on, let me just fix all that. Let me just fix all that. Okay, get rid of all this. Okay, get rid of this guy here, which means this should be a 1. I think. Yeah, 1. So this will be plus minus 1. Okay, so our two stationary points are at t equals to 1. X is gonna be 3. Cool. And then y is gonna be, let's see, 2. Oh, that's a lot better. Alright, and then when t is equals to minus 1, x is equals to minus 2 plus 1, which is minus 1. And y is equals to, let's see, this is minus 3 plus 3. Minus 3 plus 3 is 2. Okay, so minus 1 and 2. There we go. Yeah, that's much better. Okay, so let me show you the alternative method. So the other thing you do is use the second derivative to find the nature. So how do you go about doing that? Well, the second derivative is d2y dx squared, which essentially is you're differentiating dy dx. Right? Okay, but the problem here is dy dx is in terms of t. So you're gonna have to employ the chain rule again, and you sort of imagine multiplying by dt over dt. You're just multiplying by 1, so you're not actually changing anything. And then you're gonna swap the numerators, so it becomes dt over dx, and then d over dt, and then dy dx. Okay, and then you actually know what dy dx is because you worked it out earlier. It's actually, you know, this guy right here. So we're going to take that and I'm going to chuck that in here, which is going to give us 3 minus 3t squared over 2. And then dt dx is, you can actually work that out. Well, we have actually worked it out. It's actually this guy right there. So that's actually 1 over 2. And then, you know, you need to differentiate this guy here. Okay, so I'm gonna take out the constant and I'm gonna differentiate this guy, which is gonna give me 0 minus 6t. So we're gonna end up with negative 3 over 2t. Cool. So, let's look at this guy here. What is d2y dx squared now? Well, t is equals to 1, so we're going to put that in here, 3 over 2 times 1. That's going to be negative 3 over 2, which is a number that is less than 0. Therefore, this must be a maximum point. Okay, and then we can do the same thing here. d2y dx squared is equals to negative 3 over 2 times negative 1, and as you can see, it gives you a positive number. Therefore, this must be a minimum point. And there you go. That's it. So, when and where do you actually see parametric equations? Well, you actually see them quite often in physics, even though you might not realize it. An example would be, okay, let me think. Oh, or even polar coordinates, right? Polar coordinates is also like a parametric equation because you're expressing x and y in terms of the angle from the center. For physics, what's a good example I can use? Kinematics is probably one of them. Kinematics, let me see. Oh, there we go. So remember we have, let's say, you project something from a height and you throw it down, so you get a projectile motion, and you can write the horizontal displacement in terms of, you know, ut plus half at squared, right? A0 if it's a projectile motion. So now you have x in terms of t, and then you have your vertical displacement, which is ut plus half gt squared. So now you have your y, which is another function of t. So you are indirectly doing parametric equations without really realizing it. Of course, in physics, we don't really do differentiation, but later on in further mechanics, you would actually be doing that. Yeah. Anyway, that's it for parametric differentiation. So let me show you a RCA example. Let's see, which one should we do? Let's do this one. This one seems fine. There's actually not that many questions. It's only 20 questions, same as the implicit differentiation. Okay, I'll take a snapshot of this guy here, and we're gonna attempt this one RCA question. So I'll just move that here, slap that in here, and put that over here. Okay, so you're given x and y in terms of t. Find the gradient of the curve at which t is equals to 0. So we start by doing dy dx equals to dy dt times dt dx. So dy dt is going to be negative 2 e negative 2t. Right? So remember, when you differentiate an exponential function, you just get the derivative of the function and then you write the same exponential function, like so. And next we're gonna do dt dx. Okay, so let's work out what dx dt is first. So dx dt is, if you look at this guy here, you can actually use the quotient rule. So the quotient rule is going to be 2t plus 3. Differentiate t gives you 1, minus t, differentiate 2t plus 3 gives you 2, and then the denominator squared. So simplifying this, we get 2t minus 2t, get 3 over 2t plus 3 squared. And then we're going to take that and we're going to chuck that in here, but we're going to have to flip it upside down because this is dt dx, not dx dt. So we're going to get 2t plus 3, and this whole thing is squared divided by 3. There we go. So now that we have worked out what dy dx is, we can actually put in, we're going to substitute t equals 0 in there. So we're going to get negative 2e to the power 0 times 9 over 3. So that's going to give me negative 2 times 3, which is negative 6. And you are done. That's it. So as you can see, it all boils down to just using the chain rule, this one. And that's pretty much all there is to it. Very short chapter, as I've said. Okay, we're done with differentiation. Woohoo! Now for the hard part, integration. So this is the chapter that most people find the most difficult when it comes to A-level math. But it's actually not too bad if you can see the pattern. So we'll start with, let's see, we'll start with logs. We'll do it slowly. So this chapter will go slowly because this is the chapter that a lot of people find very difficult. This one and complex numbers, those two chapters. It used to be vectors as well, but they have actually changed the syllabus and moved most of it to further math. So if you're not taking further math, this is as difficult as it gets for vectors, which is, well, very easy because you don't deal with 3D vectors anymore. Dance party. Okay, right. How much time do we have? Let me see. We started at... Yeah, we still have plenty of time. Okay, good. Right. Let's take a 5-minute break and then we'll start integration. Okay? 5-minute break. See you guys in a bit. Okay, you guys ready? Let's continue with integration. Whoop whoop. All right. Hang on, let me just save this and export that. Okay, clear the whiteboard. All right. Okie dokie. So, similar to how we have done differentiation, there are actually a couple of basic rules that you can employ that all the other things are built upon. These rules you can derive using two ways. The first one is using first principles, which is extremely tedious and I wouldn't recommend doing it. And I don't think I would even show it here, but if you're interested, I have done some of it on my compendium, so I can send it to you, or you might have it already. But that involves you have to do like the summation of arbitrary powers, like 1a plus 2a plus 3a. It's very tedious, so that one takes a long time to do, so I'm not going to do it here. The other way of finding these rules is by using the fundamental theorem of calculus to use the fact that differentiation and integration are inverse operations. There's actually a proof for this as well. It's more of a geometric proof. There is a more robust proof, but that proof I haven't really looked into it yet, so I can't really talk about it much. But the geometric proof is pretty cool, though I don't think I want to show it here as well, because again, it's fairly tedious to show. So just know that differentiation and integration are inverse functions. Okay, so what we have done so far in AS is that whenever you integrate x to the power of n dx, we know that you would get x n plus 1 divided by n plus 1 plus c, where c is the integration constant. Right, this is what we know so far. Okay, so for now, you need to know that if you were to integrate 1 over x dx, you might be thinking, well, isn't this just, x to the power of minus 1? Can I just use the same, the thing that we have been doing since AS? Can I just increase the power by 1 and divide it by, oh, wait a minute, we are dividing by 0. So obviously that's not going to work. So what should we do then? Well, it turns out that if we differentiate ln x, we actually get 1 over x. So if we integrate 1 over x, we should get ln x, because they are, like I said, inverse operations, right? So what you would actually get is ln x plus c. But there's a little caveat over here. The caveat here is this x is going to be a positive value, so you have to put a modulus in there. Okay, you must put the modulus in there. Must put the modulus, remember that. Okay, cool. Now, the other thing that you need to know, because remember back in differentiation, I always show you the basic one and then the one where the x is replaced by a function, right? For example, if you differentiate x to the power of n, you would get nx n minus 1. But then you can also say, if I differentiate some function to the power of n, I would get n, and then I differentiate the function, and then I write the same function again, and reduce the power by 1. So there is a similar thing happening here for integration as well. Okay, so let me just show you how that works. Let me just move this a bit to the left because we are running out of space, and just put it here, like so. I got a message just to check to see if there's anything important. In case you guys are asking me something. Nothing. Okay, never mind. So where was I? Right. So for this guy here, wait, where's my pen? For this guy here, if you integrate some function, and then this is to some power of n, like that, you can actually say that you get the same function, and then you increase the power by 1, and then you divide by that increased power, and then you divide by the derivative of the function plus c. But there is a little caveat here. So the caveat here, or the condition here, is that fx must be linear. Linear means the highest power of x is 1. If it's anything greater than 1, this is going to fall apart and it's not going to work. Because the reason this exists in the first place has to do with a technique called integration by substitution. Okay? Which is something that we will learn soon. Similarly, for this guy here, if I replace this with a function fx and I integrate it, what I'm going to end up getting is ln and then the modulus of fx, and then I divide that by f prime x plus c. But again, the condition is fx must be linear. If it's not linear, you cannot do this. Okay, so let me show you why it has to be linear. Hang on. Oh, okay. Seems like you guys got the form for the exam, so let me just mention here which one you should choose. We should be taking, let's see, paper 1 and statistics paper 5. So 1353, which is option S9. So for those of you who are taking the exam this October, November, the option that you want to be choosing is S9, the one with 1353, sorry. Right, that's S9 1353. So you want to choose this option. Yep, that's it. Okay, so why does the function have to be linear in order to use this thing here? And how do we use this in the first place? Okay, you know what? Let me put in some. Let me do some examples just to show you what's happening. So let's say we are trying to integrate 1 over 2x plus 1. Okay. You know what? Let me just change this a bit. Let's say we have 3 over 2x plus 1. Okay, right. What we can do is we can take out the 3 because the 3 is just a constant, so we have 1 over 2x plus 1. And you can see that 2x plus 1 is a function of x. So when we integrate this guy, you would actually get this guy right here. However, you have to first check and make sure that 2x plus 1 is a linear function. So is it a linear function? Yes, it is, because the highest power of x is 1. So we can actually just use this. So what's that going to give us? Well, that's going to give us ln modulus of 2x plus 1 over the derivative of 2x plus 1, which is 2, and then plus c. There we go. And we're done. That's it, really. Okay, so how can we actually show that it has to be a linear function? Well, suppose we don't know how to do this. Okay, suppose I didn't tell you this. The only thing that you know how to do is this guy right here. So we have to use a different technique. This technique is called integration by substitution. So let's say we're going to integrate 3 over 2x plus 1. We're going to take the constant out. So since the only thing that we know how to integrate is 1 over x, but this doesn't look like 1 over x, right? But what we can do is we can substitute 2x plus 1 with a different unknown, so it looks like 1 over x. So we could say let u be equals to 2x plus 1. So that's going to give us 3 integral 1 over u. But now the problem is we are integrating with respect to x, but there are no x terms in here because they're all replaced with u. So we have to change this to du instead of dx. So how do we find du? We have to differentiate this guy here with respect to x. Du dx gives me 2. So du equals to 2 dx, which means dx must be a half du. Cool. So we know dx is half du, so we're going to just put that in here. 1 over u and then half du. Okay, so we can take out the 1 over 2 out and put it out here. And now you can see that this guy is in fact something similar to this, which means we know that we will get this guy instead. So we're going to end up with 3 over 2 ln modulus of u plus c. What is u over here? U is actually 2x plus 1. And as you can see, this is actually the same thing as what we got earlier. So this is actually a shortcut. But the shortcut actually comes from the technique called integration by substitution. Now let me show you what happens if I were to replace 2x plus 1 with a non-linear function. Okay, ready? Here we go. Oh, so let's say we have, hang on, I get this. Let's say we have integrate 3 over 2x squared plus 1. So you can see this is a non-linear function, right? So let's say we're going to take out the 3. Okay, cool. We're doing the same thing. And then we're going to say, I'm going to replace u with 2x squared plus 1. Haha. So now this looks like 1 over u dx. Oh no, there's a dx here. We have to get rid of dx, so we have to put a du in there. So let's try differentiating this guy. We get 4x. So dx is going to be equals to 1 over 4x du. Hey, there we go. And I'm going to substitute that in. So 1 over u, 1 over 4x du. Oh no. Now we end up with a dilemma because now we have an x in here and we can't get rid of it. So we can't integrate it because there's a variable in here which is not in terms of u. So we're stuck. Oh no. Therefore, you can see that it has to be a linear function. If it's not a linear function, you would always end up with some variable which with an x in there. So you can't continue. Okay? So this only works if it's a linear function. If you get a question in the exam which is not a linear function, you have to make it a linear function somehow. Usually using partial fractions, which is what we learned a couple chapters ago. Okay? So let's do a quick example. Let me show you. Do we have a quick example here? Let me see. I think the textbook has an example. Okay, there's no example in the textbook. Fine, I'll make my own example. Right, let me just move that over here. Let's say I want to integrate 1, oh, you know what, 2, let's put 2. Let's put 2 over 4 minus x squared dx. Okay, now suppose you say, you can see that this is very similar to this guy here. It's a function of x, right? But then you have to be careful because you can see the function of x here is non-linear. It is a quadratic. This function of x is quadratic, so you can't do this unless you make it a linear function. How do you make it a linear function? You have to use partial fractions. Okay, because you can see that this guy is in fact 2 minus x, 2 plus x dx. And then you can split this into 2 partial fractions like this, plus b over 2 plus x dx. So a 2 plus x plus b 2 minus x is equals to 2. So if x is equals to -2, a cancels, so we're left with 4b equals to 2, therefore b must be a half. Haha! Now if x is equals to a 2, then 4a is equals to 2, which means a is equals to a half. There we go, so we've actually worked out the partial fraction, so we have a 2 minus x here, plus 2 plus x over here, and we can factorize the half out so that we are left with just 2 minus x here and 2 plus x over here. Okay, so we have two separate integrals separated by a sum, so which means we can integrate them separately. So if we integrate this guy, we are going to get 1 over 2 ln, remember to put a modulus, 2 minus x, and then divide that by the derivative of the function, which is -1. And this guy here is a half times ln modulus 2 plus x divided by the modulus divided by the derivative of the function, which is 1 plus c. So simplifying this, we get -1 over 2 ln 2 minus x plus 1 over 2 ln 2 plus x. And then we can, let's say, we can take out the half out, which means we are left with ln 2 plus x minus ln 2 minus x. And because this is a ln and we are subtracting, we can use the rules of logarithms to combine them together, and then we get 2 plus x over 2 minus x. And that's your final answer. Okay, so this is very important. Make sure that the function is a linear function before you employ the equation that I showed you earlier. Okay, so I'm not gonna show you the other rules of integration, but because I think that might be a bit too much. So I think for now, just focus on this one. Practice on parametric differentiation, and I'm gonna give you the exercise on WhatsApp later. So if you have the textbook, you can try exercise 5a. So you can try all of that. And then for parametric differentiation, you can try 4e. Okay, 4e. So you can try these two exercises. And that should be enough for the weekend, right? And you can also do the passe questions if you are filling up for it. But yep, there we go. I think we shall stop here for today. Okay, so little announcement. This is actually my last term with you guys. So starting from September next term, someone else will take over math and physics. Yeah, because I will be leaving Kingsley. So, yep, the last day would be July 19. That's when I will bid you farewell. Yeah, just thought I'll put it out there since it's almost the end of the term. Okay, so I shall see you guys next week. We're gonna continue with integration. And for those taking physics, I shall see you tomorrow morning. And yep, bye-bye.